Hi there, this is Heath. Let's start the week 10 notes. This is orthogonality. Let's get started. When we talk about the dot product of two vectors, it gives us a scalar for a product. We can use this scalar to find the angle between the two vectors. And so there will be a process that we'll talk about in a moment that will allow us to calculate this angle if we know what the dot product of these two vectors is. To find the dot product, we're going to multiply matching components and then add results. Many of you have done this in other classes, so I'll go through this part pretty quickly. Example 147. Let's find the dot product of these two vectors. What I'll do is I'll take the x coordinates and I'll multiply them together. 3 times -4 gives me a -12. Then I'll take the y coordinates, I'll multiply them together. 2 times 1, that gives me a +2. And then I add them together to get a grand total. The grand total is -10. This is a dot product of the two new vectors. Rookie mistake. I see people do this all the time. Is that they'll multiply the 3 times -4 and they get a -12. Then they multiply the 2 times 1 and then you get a 2. And then they give me the answer as a vector -12 too. That's not right. The answer is to add them together after you've multiplied together and give me a single number and not a vector. Okay? If this dot product is positive, the vectors form an acute angle. If the dot product is negative, they form an obtuse angle. And if the dot product is 0, they form a right angle, a 90-degree angle. A lot of people know this fact, but they don't know these other two facts. If we go back to the last example that we're looking at, if I were to plot the vector 3, 2, and the vector -4, 1, it's pretty clear that the angle there is an obtuse angle, and I got a negative dot product. And the negative sign is what tells me that the angle is going to be obtuse. Okay? We know something else that does the same thing. We know something else that gives positive answers for angles that are less than 90 degrees, 0 for angles that are equal to 90 degrees, and negative answers for angles that are greater than 90 degrees. It's one of the trig functions. Which trig function is positive in quadrant 1 and negative in quadrant 2? The answer is cosine. It is almost true that the dot product of two vectors is the same thing as a cosine. That problems involving cosines we could just do with dot products. The problem is that it's not true because of units. It's not true because of units. If, for example, my axes were measured in, let's say, meters, so this is 1 meter, 2 meter, 3 meters, so on and so forth, then the cosine is equal to a length divided by a length. It's like an opposite side, no, an adjacent side, I do know the difference, over the hypotenuse, which is something in meters divided by something in meters. This side is unitless, but this is a product. It's the product of the x coordinates times the y coordinates, which is something in meters times something in meters. This side is in meters squared. These two are measuring the same thing. They're measuring the sign of the angle. Positive, negative, or 0, acute, obtuse, or right. But this is giving a unitless answer, and this is giving me an answer that's in square meters, or square inches, or square feet, or square of whatever the units are measured with. If we can correct for that unit discrepancy, then these two things become equal. And here's how we're going to fix that unit problem. I'm going to divide by the magnitude of the r vector, and I'll divide by the magnitude of the s vector. This is in square meters, but I'll divide by the number of meters in r, and I'll divide by the number of meters in s. And now this side is unitless also, and now the two sides are equal to a cosine. This gives me the exact angle between two vectors using this formula. A lot of physics books, you'll see this formula written in this formula, that the dot product is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. You'll see this form a lot. Let me get my pen to work. There you go, alternate form. I don't like this form as much because I see in this form the cosine being equal to the dot product divided by a couple of things that help cancel the units. I see what's going on over here. This is a common form of this equation, but it's not as clear to me why this formula works, but they're equivalent. I'm going to use this formula on the next example, and we're going to calculate the angle between these two vectors. This is the vector 3, 2, 0, 3 units in the x direction, 2 units in the y direction. This is the vector 1, 4, 1, 1 unit out, 4 units over, and then 1 unit up. And we're going to calculate this angle here. Now, in 3 dimensions, this is a hard problem to do without using dot products. You can use trig, but you're working in a plane that's tilted. It's not the xy plane. It's not the yz plane. You're working in a plane that's slanted. And that makes this a little hard to do with just trigonometry. Let's see how easy to do with dot products it is. Oh. The formula is that the cosine of the angle is equal to the dot product of the two vectors divided by the magnitude of the two vectors. So let's calculate the dot product. We multiply the x coordinates together. We multiply the y coordinates together. And then we multiply by the z coordinates together. And so that's 3 plus 8 plus 0 is 11. And then the denominator, we're going to take the magnitude of these two vectors. This uses the Pythagorean theorem. The square root of 3 squared plus 2 squared plus 0 squared. That's the square root of 13. And the magnitude of s, that's the square root of 1 squared plus 4 squared plus 1 squared. And that's the square root of 18. We'll divide 11 over the square root of 13 square root of 18, and we get an answer that's approximately 0.719. Then we find the inverse cosine of that. And in radians, we get 0.76 radians. In degrees, we get 44 degrees. And that gives us this angle here. It's not bad. It gives us a way of using vectors to calculate angles. We say that a set of vectors is an orthogonal set if every pair of vectors in a set is orthogonal. Orthogonal means the dot product is 0. For example, these 3 vectors form an orthogonal set. If I calculate v1 dot v2, multiply the x coordinates to y coordinates to z coordinates. The x coordinates 3 times -1 is -3. The y coordinates are 2, and the z coordinates are 1. And that adds up to 0. If I do v1 and v3, It's a little bit messier because of the fractions. 3 times negative 1/2 is negative 3/2. 1 times negative 2 is negative 2. And then 1 times 7/2 is positive 7/2. That adds up to 0 also. And then if I check v2.v3, that also adds up to 0. Negative times negative gives me positive 1/2. 2 times negative 2 is negative 4. 1 times 7/2 is positive 7/2. These two add up to 8/2, which is 4, plus negative 4 gives me 0. All three dot products give me 0, and so we have an orthogonal set. All orthogonal sets are linearly independent. We'll actually take a moment to prove this. It's not a hard proof. Let's say we have an orthogonal set, and we form the homogeneous equation. In order to be linearly independent, there could be no free variables in this homogeneous equation. That's what it means to be linearly independent. That the only solution is going to be the trivial solution. We're only going to have that one solution because there's no freedom in this system. So that's what we want to show. We want to show that all of these coordinates have to equal 0. So we're going to first show that C1 has to be 0. And to do this, I'm going to dot product both sides by the first vector. I'm going to dot product the left side with v1, and I'm going to dot product the right side with v1. And so when I distribute, I get c1 times v1 dot with itself, plus c2 times v1 dot v2, plus so on and so forth. c1 v1 dot vn. On the right side, I get v1 dot 0. But these vectors are orthogonal. And so this dot product is 0, and this dot product is 0, and all the dot products in between are 0. And anything dot product with the 0 vector will give me 0. And so the only non-zero term that I have left here is this vector itself. v1 is not orthogonal to itself, and so c1 times this vector has to be 0. But since v1 dot v1 doesn't equal 0, then the only way this product can equal 0 is if c1 is 0. Okay? So c1 has to be 0. So now that we've shown that c1 is 0, how are we going to show that c2 is 0? We're going to go through the same process again, but instead of multiplying by v1, we're going to take the dot product with v2. And then the next time, we're going to take this dot product using v3. We're going to take the dot product with vn. Eventually, we're going to end up having every one of these coefficients is going to be 0. Okay? So every orthogonal set is also linearly independent. Okay? That, by the way, should be a C sub n, not a C plus n. All right. The result of this theorem is that every orthogonal set is linearly independent, but every linearly independent set can be used as a basis. And so orthogonal sets make good bases, and that means that we can calculate the coordinates of vectors in a basis that's made up of an orthogonal set. Now we know how to do this. We learned back in week 6 that if I have a vector v, we can calculate the coordinates of v in the alternate basis by taking those basis vectors and augmenting it with v and then row reducing and solving the system. We have a new theorem that if our basis is orthogonal, then we have a shortcut. If the basis is orthogonal, this formula is a shortcut. And the formula is that we will take the vector that we are trying to calculate the alternate coordinates of and dot product with every vector in the basis, and then we'll divide it by the basis vector dot product with itself. This is the basis vector with itself. I'll show you an example in a moment, and I'll show you how fast this is compared to having to row reduce. This is example 150. I have these three vectors. We already showed that they are all orthogonal. We did this a moment ago. We already showed they are orthogonal. And when we have an orthogonal basis, then calculating v sub b, we have a shortcut for. So here's the shortcut. The formula again is we're going to dot product v with the basis vectors, and then take the basis vectors and dot product them with themselves. So let's do the first vector. V dot v1 is 18 plus 1 plus negative 8. 6 and 3 is 18, 1 and 1 is 1, 8, negative 8 and 1 is negative 8. And that gives me 11. And v1 dot with itself is 3 times 3 is 9, 1 times 1 is 1, 1 times 1 is 1 again, 9 plus 1 plus 1 is 11, 11 over 11 is equal to 1. So that's our first coordinate. So let's look at our second coordinate. V dot v2 and v2 dot v2. V dot v2 will be 6 times negative 1 is negative 6. 1 times 2 is 2. Negative 8 times 1 is negative 8. And that's negative 14 plus 2 is negative 12. In the denominator, negative 1 times negative 1 is 1. 2 times 2 is 4. 1 times 1 is 1. 1 plus 4 plus 1 is 6. Negative 12 plus 6 is negative 2. That's going to be the second coordinate. The third coordinate, this is going to be a little bit messier. This is v dot v3 over v3 dot v3. So that's 6 times negative 1/2 is negative 3. 1 times negative 2 is negative 2. And negative 8 times positive 7/2 is negative 28. That's negative 3 minus 2 is negative 5. Negative 5 minus 28 is negative 33. In the denominator, negative 1/2 times negative 1/2 is positive 1/4. Negative 2 times negative 2 is positive 4. And 7/2 times 7/2 is 49/2. Okay, 49/4, sorry. 1/4 plus 4 plus 99/4 is 1/4, and 49/4 is 50 over 4, which is 25/2. 25/2 plus 8/2 is 33/2. When we divide negative 33 by 33/2, that's the same thing as multiplying by 2 33rds, and the 3's cancel, and we end up with negative 2. And so the coordinates of this vector are 1, negative 2, and positive 2. And the linear combination is 6, 1, negative 8. This is my vector v, is equal to 1 times the first vector, 3, 1, 1, plus negative 2 times the second vector, negative 1, 2, 1, plus negative 2, put the negative 2 there also, times the third vector, negative 1 half, negative 2, negative 7 halves. And we can check to make sure that this works. This is 3. Negative 2 times 1 is positive 2. 3 and 2 is 5. Negative 2 times negative 1 half is positive 1. That makes 6. So the top coordinate checks. 1 minus 4 is negative 3. Plus 4 cancels with the negative 4. And that gives me my 1 back. So the middle coordinate checks. Bottom coordinate is going to be a little bit messy again. 1 minus 2 is negative 1. Negative 2 times negative 7 halves is negative 2 times positive 7 halves. There's no negative sign here. Is negative 7. Negative 1 minus 7 is negative 8. So the bottom coordinate checks. And so we're able to calculate a linear combination of vectors, but we had no row reduction. We did this entirely using dot products. And that's a lot faster. So we're able to calculate the alternate coordinates of v using dot products instead of row reduction. That process is a lot faster, but it only works if b is orthogonal. So I want to ask this question. Is it possible just to take an ordinary basis and make it orthogonal? Is there a way that we can turn some basis that's not orthogonal into one that is, so that we can take advantage of this shortcut? And the answer to that question is yes, and that's what we're going to look at in the part 2 of this video. Take care.